Welcome to lecture 9 in GRA 6036. Today is Thursday, March 19. In this lecture, I'll start by saying something about hypothesis testing. Then I'll say something about interaction terms. Both things are relevant for the project you are to work with today. I know that you in Bergen, you might have done hypothesis testing already, so if you feel comfortable with it, you can skip ahead to the interaction terms videos. Well, so let's start out by coin flipping. Now, say you toss a coin 8 times and we get heads, that's 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So we get in 8 tosses of this coin, you get one tail. Now, you all, if this is what you obtain in 8 tosses, you would probably think that, well, this coin is not fair. So, I mean, when we see a coin, we typically start out by thinking, well, it's a 50-50 chance of it showing head or tails when we toss it. But if this is what you get in 8 tosses of a coin, you might stop thinking that you are dealing with a fair coin. So that is basically the idea behind testing hypothesis. So when we first meet a new coin, our hypothesis about the world, about the state of affairs, about this coin is that it is fair. So if we denote by p, small p, so let p be the probability of getting heads, then our baseline hypothesis about this p, what we call in statistical language the null hypothesis, is that this p is equal to 1/2. Then the coin is called fair. The alternative to it not being a fair coin is that it's an unfair coin, so the alternative hypothesis is that this small p is not equal to 1/2. And well, if you toss the coin 8 times and you get this sequence of heads and then one tail, you might stop thinking that this is true, and you change your mind to well, p does not equal 1/2. This is not a fair coin. In statistical language, that means that you reject the null hypothesis. Okay, so let's think about why would these data, because that's what they are, make you reject this null hypothesis? Well, because because if you assume that the null hypothesis is true, which means that you assume that p is equal to 1/2, then obtaining the sequence, let's call this sequence star, then you have at least you have this feeling that obtaining star has a low probability. So you're not really likely to obtain this sequence if indeed p equals 1/2. Now, these being so-called Bernoulli trials, we can compute the probability of getting star under the hypothesis that p is equal to 1/2. So let's do it. So the probability of getting, assuming that p equals 1/2, the probability of getting a heads on the first here is 1/2. The second, it's 1/2, and so on. The 7th, it's 1/2, and of course, when the probability of getting a heads is 1/2, the probability of getting a tails is 1/2. So this is then equal to 1/2 to the power of 8. Now, so this is the probability of getting this sequence of head or tails, which is a small number, a very small number indeed. I mean, I can, well, let's, so what is 2 to the power of 8? 2 to the power of 8 is 256. So this is 1 over 256. So, well, the probability of getting star is small. But of course, I mean, it wouldn't, you would feel the same about this coin whether the T is the last toss or if the first one. I mean, the point is that just getting 7 heads and 1 tails makes you doubt that this null hypothesis can be true. So we can also compute, so let's compute the probability of getting 1 tail. So the probability of getting 1, so exactly 1 tail, is the probability of getting, well, such a sequence. But this T can be in 8 different places. So then it's just to multiply 1/2 to the power of 8 times 8, which is, so I'm having R on my side here helping me out doing these calculations. So it's 0.03125, which is a small number. So the point here is that under the hypothesis that you have a fair coin, the probability of obtaining a sequence such as star is small. Therefore, you stop believing that this can be true. So you reject the null hypothesis. You still haven't really made up your mind about what you should think about P, other than that it's not equal to 1/2. But you probably stop believing that it's 1/2. So this is the intuition behind all hypothesis testing. And in the next video, we'll translate this to a regression example.